perspective, how many possible outcomes are there in which you have two heads actually. So these possible outcomes are 3. But if I want to calculate how many possible orderings you have, how many patterns you can have in which you have 2 heads and 1 tail. So you are saying that out of 3 you have 2 heads actually. So if I say that let O be an ordering, of k successes, so it's one particular order, like this, or like this. It does not represent all orderings. So it's an abstract ordering, concrete one ordering of k successes. Okay, k successes. Then I want to know what is the probability of an ordering, a particular ordering, given that there are k successes. So O is a one particular ordering in which you have k successes and n minus k failures. Now I want to compute the probability of a particular ordering, given that in that ordering there are k successes. Now I can compute this through conditional probability. So this would be equal to probability of ordering and give x equal to k divided by the probability of x equal to k. Okay. Divided by probability of x equal to k actually. This is not going to be 1/2, 1/2, and 1/2. Oh yes, it's going to be 1. Yes. Okay. So k successes. Now this is an event. So try to make sense of this event. That what does this mean? O means one particular ordering, and x equal to k means that there are k successes. This is kind of representing all possible orderings that you can have in which you have the k successes, and O is the one of the ordering. So this must be a subset of this actually, because this contains all possible orderings, and out of all these possible orderings, O represents one ordering actually. Okay, it's one ordering. So O intersection this event should be what you call probability of O given divided by the probability of x equal to k. Okay, so probability of O divided by the probability of x equal to k. Now what is the probability of this? Probability of O. Okay. What is the probability of O? The probability of O, so O is like, say for example, first k successes and then n minus k failures. So this is just one kind of a thing actually. Okay, so it's a fixed ordering. So what is the probability of fixed ordering? So just simply multiply that how many heads you have and how many tails you have. So simply this. So O is an ordering in which you have k successes. So this is going to be p power k. And n minus k failures, so it's going to be 1 minus p n minus k divided by what is the probability of k successes? So this includes like all possible orderings. So you're going to say that okay, so it's going to be n choose k. So this is the total number of possible ordering times p power k and 1 minus p power n minus k. So obviously all this is equal to 1 over n choose k. Okay, so this is the required probability, okay, of a particular argument. So what does this interesting example shows that yes, using the conditional probability in conditional PDF, what you concluded is that if in a given number of trials the number of successes are fixed, then all such outcomes in which you have, say, that fixed number of successes, say for example k successes, each one of that outcome in which you have k successes is going to have an equal and exact probability. All outcomes are equally likely, and that probability is 1 over n choose k. Okay, so this makes a bit of a sense. Now let me move towards, say, the joint continuous time case. Okay. Continuous time case. Continuous time, continuous joint conditional PDF, conditional distribution, Now the outcome is going to be same, the basic definition is going to be same, that the conditional PDF of x given y, where x takes the value x and y takes the value y, is equal to the joint PDF of x and y divided by the marginal PDF of y. Okay, this is what the case actually. Now you can say that if I'm interested in computing, say A and B are two subsets of R, they are two subsets of R. Points don't make sense more in the case of the continuous time case. So it's better to talk about the sets actually and say I'm interested in what is the probability that X belongs to a set A and Y belongs to a set B actually, and this is what they're going to do. So what you can do, say Y is equal to a fixed number Y. So X is in some set and Y is fixed Y. So how you can compute it? So what you can do is that you integrate the joint PDF, the joint conditional PDF, okay, over the region A. Over the region A. Okay. So what is the probability that X belongs to a set A? It's not equal to one value, but a set of values, given that Y is Y. So what you can do is that take the conditional PDF and integrate it, say, with respect to what is called X actually. Okay, because X is variating, Y is fixed. What would be the joint CDF? Say X given Y, where X takes the value A given that Y takes the value Y. So this should be equal to what? Probability of X less than or equal to A given Y is Y. Okay. And from above formula, now the set A, X less than or equal to A means that X belongs to a set A that is negative infinity to A. So if X belongs in this interval means if X less than or equal to A. And how can I compute this probability? That take your CDF, PDF, conditional PDF, and integrate it over this set. And what is this set? So start from minus infinity and at A, okay, and at A, and integrate the joint PDF. with respect to dx. So this is what it is going to be. Okay? So this is a complete particular case of it. So once again, the joint PDF has a similar definition of conditional PDF, conditional probability distribution function as discrete case, and instead of saying that, because in continuous time it makes sense more to talk about the set, okay, of the values rather than, you know, one particular value. So if A is a subset of R, then what is the probability that X belongs to A given Y equal to Y? Take your, you know, what you call CDF and integrate it over the region, over set A with respect to X actually. Okay? And this is what is the CDF actually. So let's do one example. Let's do some examples. The example is that suppose that you have two random variables x and y whose joint PDF looks like this. Okay, so you have two random variables whose joint PDF looks like this. So it is equal to say 12 over 5 x times 2 minus x minus y, where x is sitting between 0 to 1 and y is also sitting between 0 to 1. Okay? N equal to 0 otherwise. It's equal to 0 otherwise. Question is, what is the conditional probability? Okay? What is the conditional probability? It says that compute the conditional density of x given y. This is what that it says actually. So compute the conditional density x given y where the y is between 0 to 1. This is what that I would like to do. So how can I compute it? So in order to compute it, okay, what would be the solution to that? So I need to compute, say, fx given x given y as what f of xy divided by fy of y. Okay, this is what it is. Now f of xy, we know that if x and y are between 0 to 1, okay, if x and y are between 0 to 1, x is between 0 to 1 and y is also between 0 to 1, then this is non-zero. Okay? And it is equal to, what do you say, 12 by 5 x 2 minus x minus y. Question: how can I compute the marginal PDF of y? So marginal PDF of y can be computed by integrating the joint PDF with respect to x actually. So let's integrate it. Integrate it from where to where? Obviously integrate it only in this interval, because outside these intervals it's 0. So integrate 0 to 1, what do you call f of x, y and dx actually. Okay? So this is what it is going to be. And if your x and y are between 0 to 1, then the integral is going to be 12 over 5 times x minus 2 minus x minus y, and integrated with respect to x. So it's a pretty simple integral. So this 12 over 5, 12 over 5 will get cancelled. X minus 2 minus y given this integral, you can solve it yourself, is going to be equal to 4 minus 3y. So this is the conditional PDF of x given y when x is in the interval 0 to 1 and y is also in the interval 0 to 1 actually. Okay? So I substituted CDF and divided by the marginal, what do you call, PDF of y. We computed it and turns out to be 0 to 1. We're going to say that okay, so this is true when x is between 0 to 1 and y is between 0 to 1, and obviously this is equal to 0 otherwise. So that's, this is the conditional CDF of x given y, formula for it. Next that I would like to talk about is the joint probability distribution of function of random variable. So the joint distributions for functions of random variable. Functions of random variable. Okay. I mean, recall, we know in one dimension, if x is what do you call, is a random variable with a PDF x, and I have a random variable, so x has PDF fx, and y is some monotonic function actually, increasing, decreasing. So it's a kind of a function that is roughly invertible. Then the PDF of y with respect to x, okay, is equal to what do you call fx evaluated at g inverse of x times the absolute of g inverse of x divided with respect to x. I mean, if you remember, we had this formula in one dimension actually, that okay, if x is a PDF fx and you have some function of x, some nice function of x, and this we call it, for example, give it a name y. The question is, what is the PDF of the y? So we derived actually, and we proved this formula previously, that the PDF of y of x is going to be fx evaluated at g of x times the absolute of the inverse of the g of x with respect to dx actually. Now what we like to do, we will like to do the same but in 2 dimension and maybe in higher dimension as well. Okay. So imagine you have 2 random variables x1 and x2, be random variables with the joint PDF, let's call it fx1, x2. Okay. Now imagine I have 2 functions y1. y1 is a function g1 of x1, x2, and y2 is function g2, x1, x2, okay, of x1 and x2. The question is, what is the joint CDF of y1 and y2? This is what that we would like to have actually. Okay. Now, here are some assumptions on G. Okay. Here are some assumptions on G. So the G1 and G2 should follow these conditions. For example, here, what was the crucial assumption? When you can have this Fy of x when G is invertible. So if you can invert G, then you can apply, then you can compute its, what do you call, conditional, or not conditional, but the CDF of the y. The same should be the case here actually, that you should be able to invert it actually. Okay? In other words, In other words, if you have equation y1 equal to g of x1, g of x2, and y2 equal to, say, g of g1 of x1, x2, and y2 equal to g of x1, say, x2, then, okay, we should be able to write x1 and x2 in the terms of y1 and y2. In other words, then there must be functions, say, which are inverses of g1 and g2 actually, say h1 and h2, such that x1 is equal to h1, y1, y2, and x2 equal to h2, y1, y2. So they should be invertible actually. Okay. The second assumption that they should have, and it should be very much analog to what you have here. So think about it. First, in one dimension, inverse should exist. Second, that inverse should be differentiable. So you should be able to compute the derivative. For example, inverse exists, but if you are not able to differentiate it, you can't find the joint CDF of y. So here we said that g1 and g2 should be roughly invertible. You should be able to write x1 and x2 in the terms of y1, y2. So, and the secondary, important question is that that h1 and h2, okay, should have constant, or g1 and g2 should have continuous partial derivative. Moreover, second assumption on g1 and g2, that g1 and g2 have continuous partial derivatives, okay, continuous partial derivatives, such that we can calculate the Jacobian of g1 and g2. So this is what essentially, such that we can calculate what this Jacobian function of x1 and x2, which is basically what you also have this notation for Jacobian g1 and g2 with respect to x1, x2, partial x1, x2, which is basically the determinant. What is the determinant? Partial g1 by partial x1 and partial g1 by partial x2 and partial g2 by partial x1 and partial g2 by partial x2. This determinant must be non-zero. So you can, if you have been given two random variables whose PDF is x1, x2, fx1, x2, and you have been given two functions y1 and y2 whose PDF is g of x1 and g of x2, and then g1 and g2 satisfy these two conditions, that g1 and g2 can be inverted. In other words, as y1 and y2 are expressed in the terms of x1, x2, similarly x1 and x2 can be written in the terms of y1, y2 using some function h1 and h2. Second condition, like in one dimension, that g1 and g2 should have continuous partial derivatives, okay, and this determinant, which is the Jacobian actually, should be non-zero. If you have these conditions, then here is a formula, direct formula for computing the joint CDF of y1 and y2. And it is really analog to what you have here actually. That you compute your PDF at inverse of g and multiply it with the derivatives of the g actually. So here you're going to do what? That you compute the PDF of x1 and x2 at h1 of y1 y2, which is the inverse of g1 roughly, and h2 of y1 y2. Okay, so this term is like this, and multiplied by the Jacobian of what do you call Jacobian of this function, not just the Jacobian, but the reciprocal of the Jacobian actually, P1 Jacobian, reciprocal of the Jacobian actually. Okay, so this is what is the formula for computing what do you call the joint CDF of y1 and y2, which are the functions of x1 and x2. So very simple. So it's very much analog to what you have here actually. Okay, so this is a particular case of what you have here. So now one of the important thing is that as for computing the CDF, you need G inverse of x and fx, and evaluate fx at G inverse of x and calculate its derivative. So for computing the CDF of function of random variables, you need these two quantities, h1, h2, and Jacobian actually, and obviously f of x1, x2. Then evaluate that at h1, h2. Okay. So let's do one example and try to compute. The probabilities. So here is an example. Imagine x1 and x2 are to PDF with the joint CDF fx1, x2. So x1 and x2 are two random variables.